Hi, so this is the third video in a series of 3 that I'm making about the NM series NuTone Intercom master stations. And this video is going to look at the most common problem that we've seen with the NM series since it came out. And that problem has to do with the failure of the backlight for the LCD display screen. So this is the NM100 that I showed in the first 2 videos, which if you haven't watched, you probably should if you want to get a good overview of the system in general and of the boards that make up the master station. But in this particular one, we're going to look at the backlight problem and see if we can repair it. So this is a complete NM100 out of its faceplate. I just have the 3 boards plugged together and I have it powered by a transformer for it. And this is the backlit LCD display screen that you see through the front of the faceplate. And right here is the LED light strip. I've removed this from where it was originally installed. When it's installed, it sits back behind this clear plastic housing. This would be like a light pipe. The LEDs shine into the plastic and the light travels across the back of the display and lights up the segments that are energized. And the common problem on these is the backlights fail. And without backlights, you can't really see what's on the display. You can't really judge the brightness of the screen in this video because the camcorder has much greater sensitivity to the segments than what you would see in normal room lighting. So you have to trust me that when the backlights fail, in this case they're not even connected to the light pipe, so this is just reflective light and the sensitivity of the lens. You really can't read it from across the room. In fact, you can't really read the segments if you're standing right in front of it. The LEDs are really necessary to do that. The problem that happens is customers report that the LEDs just fail and you can't read the information. So we're going to see why that happens today and see if we can actually repair this particular one. So let me show you what I've actually discovered about the problem and then let's see if we can get it fixed. So here's a close-up view of the LED light strip, and there are 2 power wires down here on the bottom, a red and a black. And then there are 2 LEDs. We have LED 1 and LED 2, and these are miniature surface mount LEDs, and the light comes out of the side of the LED assembly, so it's shooting off to the right and then into the light pipe. And this is a powered up NM100 right now, and it would look as if these are not on at all. But I'm going to go ahead and change the camera setup here a little bit and let you see what's really going on. So what I've done is I've turned off all the lights in the lab, and I've covered with a dark cloth, I've covered over the top of the master station and over the front of the camera, and you can now see in the darkened environment where the LED light strip is located, you can actually see that the LEDs are actually on. They're the 2 little bright spots. It's going to be hard to point to them because I can't really see it, but if you follow the screwdriver, which is moving around here, here's one right here. I'll cover it up a little bit. That's the lower LED, and there's the upper LED. So you can see that they actually are on. In normal room light, you really can't see it very well. And the other thing to consider is, as a feature of the NM100, there are 3 brightness settings for the LEDs to change the display brightness, and you do that by operating the buttons on the front of the unit, which I'm going to try to do here in the dark. So you have to push the tuning up button and the power button at the same time, which I'm going to do now. And so that's the low setting, the medium setting, and the brightest setting, and then back down to the low setting. So we actually can see that the LEDs aren't out altogether, but they're not putting out the amount of brightness that they're supposed to, and you can change the brightness, but even on the highest setting, it's not enough. So now the question is, why is that the case, and what can we do to repair it? So let me get things set up and let's see what we can find out. Okay, so the first thing we have to do to try to solve the problem is to figure out what's causing the problem. And since there are no service manuals or schematics for the NM series, we have to try to deduce how the NM100 master station is operating so we can try to deduce where the problem is likely to be, and that way we can try and attempt to repair it. Since there's little documentation, we have to rely on what we can observe and test and measure and figure out what it tells us about how the NM100 series is designed. So one of the things we know for a fact, because we saw it in video number 2, is that the NM100 and the NM200 are controlled by a microcontroller. Okay, so the microcontroller is like the brain of the system. It's like a small, low-powered computer. And in the microcontroller are instructions or firmware that make the master station operate the way it does. So when you ask the master station to do something, let's say you walk up to it and you want to listen to the radio, when you push the power on button, it's not like flipping a light switch on in a room to turn on a lamp. When you walk into a room and flip on a light switch, you're making a mechanical connection by moving the switch. Electricity flows through the switch and it lights up the light bulb in the lamp. That's not how devices with microcontrollers work. When you walk up to your NM100 master station and you push the power button on, what you're doing is by pushing the button, you're launching a series of instructions that are programmed into the microcontroller, and the microcontroller says, hey, somebody wants to listen to the radio, I have to turn on now, and it follows the instructions that have been programmed into it to make that function happen. It isn't any different when you want to change the setting of the lights, because you're operating the controls on the front of the master station, and the controls that you're operating are the tuning button up, and over here you have the power button, and you push both of those together at the same time to scroll through the 3 different settings for the LED lights. And those 3 settings are, we have low, and then medium, and then high. And once you reach high, if you push it again, it goes back to the beginning and starts over again. Obviously, that's being controlled by the microcontroller, so the microcontroller plays a role in this. So it could be that the reason that the LED lights are too dim are because the microcontroller or the devices between the microcontroller and the LEDs aren't working correctly, or it could be that the microcontroller is misinterpreting what the instructions are telling it to do, or it could be a problem with the LEDs themselves, or it could be a combination of all of those things. We know that for the most part, because we saw that the LED lights are actually on, but they're very, very, very dim, but you can scroll them through their low, medium, and high settings, and the intensity of the LEDs does change. That tells me that the microcontroller is probably okay. Microcontrollers don't generally control devices like the LEDs directly. There'll be other components in the circuit in between here and here that actually do sort of the heavy lifting of making the instructions actually happen in the real world. What goes on in the microcontroller, it's like software on your phone or on your computer. It's not really real world stuff. The real world stuff happens after this. I don't think it's a microcontroller problem. It's obviously not a button problem. So that leaves devices unknown in between the microcontroller, and over here we have the LEDs. The other thing we have to think about is, how is the microcontroller actually, through the other mysterious devices for now, how is it actually controlling the brightness of the LEDs? And that's something that we do know about, because it's a fairly common type of control circuit that's used in modern electronics. Back in the old days, when you had lamps with variable intensity where you could set them from low to high before LEDs, it would normally be done by raising or lowering the voltage that went to the lights through something like a dimmer switch, which you would have on the chandelier in your dining room, and you could turn the knob on the wall and change the intensity of the lights on the chandelier. And in small devices, you might have a mechanical switch that went low, medium, and high, or you might have a small switch that is variable from low to high as you turn it. And most of the time, because they were simple circuits and they were simple incandescent devices, and incandescent devices are basically just a light bulb. So we have a wire, we have a filament, and another wire, and the more voltage that you add to it, the brighter it gets, and the less voltage, the dimmer it gets. So that's pretty easy. LEDs don't really work that way because LEDs are a solid state device. It's not a filament that glows because of electricity flowing through it. They have what's called a threshold voltage. They're designed to work within a certain range of voltages. So for instance, an LED might not come on until it receives 1.5 volts of power, and it might have a maximum rating of 4.5 volts. If you go lower than 1.5, it won't turn on, and if you go higher than 4.5, you'll burn it out. They're designed to work within a specific range, and it varies a lot based on the application, the kind of LEDs, the size of the LEDs, lots of different factors. You know, in today's world, there are thousands and thousands and thousands of kinds of LEDs you can buy, and you have to choose the right one for the application. How does the microcontroller, through the mystery parts, control the brightness? Well, it probably does it by varying the voltage to the LEDs within the specified range that they're designed to operate in. And we know how that's commonly done nowadays because it's how it's done in most modern electronics, and it's done in what's called a PWM circuit. And PWM stands for pulse width modulation. And that sounds really, really fancy, but it really, really isn't. It's actually really, really simple. PWM circuits are very common nowadays, and the way that it works is very simple. You have a voltage at the beginning, and then the voltage raises up. It stays high at a certain amount. It travels over. This is the pulse, this is the width, and then it drops back down, and it goes across the bottom, and it goes up, and it does this. And it does this incredibly fast. You could possibly have, between the starting point and here, it might do it 1,000 times a second, or it might do it 10,000 times per second. And it does it so incredibly fast that when you just look at it, you can't see it. It's faster than what you can see with the naked eye. And by switching the power, basically what's happening here is you're switching the power on. It stays on for a brief period of time, and then it turns off. And then it waits a brief period of time, and the power turns on again, and it repeats over and over and over. By switching the power on and off and on and off and on and off and on and off at an incredibly fast rate, you're reducing the actual voltage. So if your voltage in is 10 and your cycle is 50%, which means it's on 50% of the time and off 50% of the time, the voltage that you get out of the circuit is only 5 volts. By changing the cycle, the number of times that it's on and off and on and off and on and off in a single second will vary the amount of voltage that comes out of this end. So you can adjust, so the microcontroller through the mystery parts can control the voltage that's being sent to the LEDs to make it more or less, and the greater it is, the brighter it's going to be, and the less it is, the lower it's going to be. This is a very common type of circuit. It's used in almost all modern electronics with LEDs for brightness control and other features like that. So we know how the circuit is probably working, but we do need to verify that, which isn't terribly hard to do. And then we need to look at and figure out what the mystery parts are, and then try to locate them on the board to take a look to see if they're working correctly. And with all of that information, we should hopefully be able to figure out what's going on. So now let's go back to the real world thing and look back at the NM100. Okay, so here's what I've done. I've soldered on a couple little yellow wires to the power connections on the LED strip, and then I have the yellow wires connected to my oscilloscope probes so we can read and look for signals that are coming in on the power lines. So let's go ahead and take a quick look at the oscilloscope and see what it shows us. So here's what we're looking at. We're looking at our PWM signal, and I'm going to stop this. So what we have here is the low volt or zero voltage. I haven't actually measured it yet. And then the voltage rises up here. Here's our width at the top, and then it drops back down, and we have a period of time when it's off again or low, and then up and on again at a higher voltage. And for some reason we have all of this noise in here, and then it repeats. The noise could be because of the flaw in the master station, or it's some other type of noise that the oscilloscope is picking up. So what I'm going to do is I'm going to run this again, and what you need to watch is you need to watch the width here at the top when the voltage is high. I'm going to scroll the brightness setting on the master station. Right now we're at low, and I'm going to scroll it to medium and to high, and if this is working the way I think it does, each time we scroll it, the width of the high point will become wider and wider, showing that it's high, the voltage is high for a longer and longer period of time, which is what gives us our increased voltage to make the LED brighter. So let's go ahead and start this. So right now the LEDs are on the low setting, and I'm going to switch it to medium. And you can see immediately how the high point of the signal became about twice as wide as it was at the low setting. And now we'll scroll up to the high setting, and it became even wider than it was before. So the brightness of the LEDs is being controlled by a PWM circuit, and the PWM circuit most likely is working correctly, which tells me, or at least fundamentally correctly, because we still have all of this noise in here. This square wave, which is a rise, a plateau, a drop, a low plateau, and an up and down, it should be uniform across the whole screen. It shouldn't have all of this noise in here. So that could be an indication of part of the other problem. So now that we know that it is a PWM circuit, we have to look at that, try to figure out what's wrong with it, see if we can fix it, and make the backlights work properly again. Okay, so a little bit of time has passed. I spent that time looking over the main circuit board, trying to figure out the circuits that have to do with the PWM that control the brightness of the LEDs, and as you can see, now it works. So what did I find? Well, first let's look at how it works. So right now, same NM100, these are the LEDs at the low setting, and I can go ahead and set them to medium and high. and you can see that's drastically different than what you saw in the first part of the video. This isn't even in the darkened lab. I don't have the workbench lights on. I could turn them on, and even with that, it's not as dramatic. But the overhead lights are on. It's not covered up with a cloth or anything like that. It's just out in the open, and you can see the LEDs. Problem solved for this NM100. Let me show you basically what I found. Okay, so here's what I found wrong. And no, I didn't find a dime in the intercom. So what I found were 2 or 3 failed components, depending on how you want to count them. I did find that the LEDs themselves on the LED strip here have failed. They're not dead completely, but they don't have the proper light output. The other thing I found was a failed transistor. And to give you some idea of the scale of things, that's why I put the dime here. So here we have a standard Liberty dime. Here we have one of the LEDs. Here we have, just for a point of reference, this is a standard transistor. This is the old school transistor. It's a TO92 package. It's a real standard size with the 3 legs and all of that. And now I'm going to show you the transistor that I found on the board that failed. And I guess we'll put it here next to this one. This transistor does the same job that this one does. The difference being this is what's called a through-hole part because it has legs and it goes on holes that go through the board and then is soldered in place. This is what's called a surface mount transistor. It's about the size of half a grain of rice. And you can scale it compared to the dime because we all know how big a dime is. And you can also see that this is about, oops, this is why you have to have tweezers so you can pick it up. And if I put it here next to one of the LEDs, it's actually a little smaller than the actual LED. This is what would be referred to as welcome to modern electronics. Components keep getting smaller and smaller and smaller, and it makes it more and more difficult and challenging to work on equipment sometimes. Removing surface-mounted components requires some specialized shop equipment to desolder and resolder them, and I was able to do that. So I scavengered a transistor off of another board because I don't have components for these in stock. I do actually have LEDs in stock because the last time I made a parts order, I sort of had already previously guessed that that could have been part of the problem, and I don't have a lot of spare LEDs floating around the shop. These are small surface mount packages also, but as you could see in the previous shot, now it works. The moral of the story is backlight problems, NM series NuTone Intercom Systems, totally repairable. Is this the only reason that they fail? Is this the absolute cause of every single one that goes out? I don't have any idea. This is only one that we've worked on. Until we've worked on 15 or 20 or 25 of them and we see the same problem over and over again, it's not a certainty, but it seems pretty likely. Why did the LEDs actually fail? Well, I think that the transistor has something to do with it. The transistor is part of the PWM circuit, and when the transistor failed, at some point it may have fed too high of a voltage to the LEDs. Remember on the whiteboard we talked about LEDs have a voltage range that they'll work in, and I think the range we used on the whiteboard was the low end was 1.5 volts and the high end was 4.5 volts. If you feed too much voltage into the LEDs, it can damage them, or if it's excessive, it can burn them out, and I think that's why the LEDs failed. The other possibility is they're either underrated for the application that they're being used for, or they're poor quality and they just don't last. So all of those are possibilities. Until we see a larger sampling, it's hard to know for certain, but at least we know that it is repairable on some level. So that's all for today. NM series backlight problem solved. I hope you found this video to be interesting and helpful. If you have an NM series with a backlight problem, you can get a hold of me. We can probably take care of it for you. If you found this video to be helpful, please give it a thumbs up on YouTube. All the thumbs ups help. If you want to subscribe to our channel, we would appreciate it. Subscribing raises our search rankings on YouTube, and that means more people find our videos and we can help them with their problems with their NuTone Intercom systems. That's all for today. See you on the next video.